Okay, so as already mentioned, the statistical innovation that the international jury has selected as the winning contribution this year is the false discovery rate and methods to control it. With main contributors, Yoav Benjamini, Joseph Hoogberg, who passed away in 2013, and then Daniel Yekutieli and Ruth Heller. Sorry. I will not say more about the winning contribution because the three laureates are here, of course, and they will give each a presentation about their work. So we'd like to invite Yoav Benjamini as the first speaker.
Okay. Okay, I'll say words of thanks later, so let me get directly to the false discovery rate and what is it, the false discovery rate story. There will be 3 talks, 3 speakers. Even though we work together in various ways, there are 3 individuals, you will hear 3 styles, and you'll see the diversity of the area, but also a single story along the way. So I will talk about discovering the false discovery rate. Ruth Heller will talk about FDR for applicability and conformal inference, and Daniel Yekutieli will speak about family-wise error rate, or FWER or FDR. That is the question. So let me start with an abridged history of making scientific discoveries. Well, we know it all started with the Enlightenment, with people like Descartes and Francis Bacon that you see here, where relying on observation and experimentation was fundamental for discovering the world. But it was Boyle later that actually made the practical way of doing this. Boyle argued for transparency. An experimenter have to state exactly what he was doing, write it down in English, not in Latin, so others will also be able to understand, including the servants that actually performed the experiments. And that was a fundamental issue. We now call it transparency or reproducibility, but that was his idea. The second issue that he brought was to replicate the experiment again and again, because the result of experiment is always uncertain with noise and not exactly precise. You have to go again and again and do it. How many times do you have to replicate it? Well, according to Boyle, it was due to the Royal Society, members of the Royal Society, who will decide whether it's enough or not. He founded the Royal Academy, so that was a good way of deciding that an experimentation is enough. But it was a dispute between Boyle and Huygens about the big science of the time, which was the air pump, that you see it right here. You see Boyle and the air pump there. That was the big science. There was a machine in London, and there was a machine in Amsterdam that Huygens built, and he discovered a new effect there. And he wrote about it, and Boyle tried to replicate it, and it didn't work. And Huygens realized that if he doesn't go practically to London and performs again the experiment in the other laboratory, no one would be convinced, especially Boyle will not be convinced. And he actually did the 3-month trip and replicated the experiment after a few failures by Boyle's machine. And it was then that actually replicability by others became the gold standard of science. That is, if someone can replicate what you did, that means that you have established a better way. And indeed, Ruti will talk about replicability in that sense. I will follow my presentation with this example. This is a very nice experiment. Goes back to 79, deficits in psychological and classroom performance of children with elevated dental levels. Lead is known to be a very dangerous material, and it was forbidden in many ways, but traces of lead, or lead was still used by the industry, and traces could be found here and there. And Nidelman was interested in knowing how much this affects the psychological classroom behavior and so on. And he did a nice, very clever experiment. He took the shed teeth of children at the age of 6 that fall, ground them, found the lead content, and then took the high-level lead and the lower-level lead and tried to compare various effects between the 10. So you can see, for instance, the classroom teachers assessed that among the low-lead group, there was 10% disorganized pupils and 20% among the high-level lead. Okay. What about it? Is it a good enough evidence? Is it convincing? 1 out of 10 versus 2 out of 10? It's not really convincing, right? This single one. So let's follow Boyle and replicate again. So if you have now, what about 6 out of 58, which is about 10%, and 10 out of 100? Is it enough? We had to wait a couple of 100 years until ideas began to form out and a way to assess this came out. I will quote Fisher, but it was already beginning with Pearson and so on before that. And the idea was to look at structured skepticism. That is, let's assume that there is no difference in lead. That actually what we see is this because it's divided randomly to two groups, and what you see, what you observe. Okay? So let's assume there was no effect of that. How surprised will you be with the 10%, with the 10% versus the 20%? How surprised will you be? We will obviously be more surprised if there will be 30% and 0%, and less surprised if it will be 14% and 15% and 16%. But how shall we deal with it? And Fisher's formulation was to calculate the p-value, which is under this assumption. What is the probability to get a result as surprising as we got, or even more surprising than that? And this is called the p-value, the problem is, and it was used, and the problem with the p-value is replication. How would you replicate, get the same result again, where the p-value is random and it will never be exactly the same in the next experiment? So that's why Fisher looked at setting a threshold, say 1 in 20, namely 5% or 0.05 that I've used, and you consider what we call now statistically significant result if the p-value is below this level. And it's interesting to note that the invention of significant test was because to address the issue of replicability. Now it is condemned for problems of replicability, unnecessarily so. So going back to our example, we see that we get 14.14. That's still not convincing result. But he did more than that. He looked at more than 35 different differences. Okay, disorganized, hyperactive, impulsive, and so on, and then IQ measurements, and so on and so forth. And among the 35, you have 20 statistically significant at the 0.05, that the p-value was small enough to be convincing. So this was a strong alarming result, and therefore the lead using industry tried to fight with it. And one of their arguments was that with 35 comparisons, the probability of an error increases and increases to the point that you can't rely on the 0.05 that was used before. And this is the problem of multiple comparisons. The problem of multiple comparisons goes back to the 50s, and two people told it as John Tukey and Scheffé, and they were arguing for controlling the family-wise error rate. That is, if you have 35 things, you want the probability of making a mistake even in one of them to be less than 0.05. Very strict requirement, and it worked well. Let me give you one of these examples. As simplest is Monferroni. You take the 0.05, you divide by 35, and it has to pass this threshold. Okay? This is the simplest of the things that control the family-wise error rate. Okay, that means that everyone, and Danny will talk more about this issue of the difference between the two and when one is more relevant than the other. But with 35 differences in Needleman's example, we should work with 0.05 divided by 35, and that's a very strong level of evidence that you need. And only 2 differences actually clear the bar. And these are the 2 differences here. And they're not that convincing. It's about delays in block and so on. I mean, you wouldn't rule out lead at all because of these 2 differences. Okay? So that was where I entered the team. And this is my experience with selective inference. It's related to Yossi Hochberg. Yossi Hochberg was an expert in multiple comparison procedures. He has the fundamental book with Tamhane from '87, which is still has important information. When he was the head of the statistical laboratory, he was responsible for a large clinical trial. And 2 blood pressure medications were compared by some 100 plus quality of life outcomes. I mean, do you wake up at night? Do you have problems of concentration and so on and so forth? Controlling for multiplicity with family-wise error rate was the best of his method, including his own, yielded nothing. It's really too much. So realizing that we started to look for ways, and that's where I entered authority. We started to look for ways. And the first one was that if you really know that only part of them are potentially true, and you can bound the number of false discoveries by MFS, M naught, then you can actually divide the 0.05 by that number rather than by 35. But you have to know what it is. Now, the point is that with large problems, you can try to estimate it, because you have many things that will not reflect any difference. And that's what we did at that time. But in '89, Yossi read a paper by Zorich. We said if only 5% is used for statistical significance in medical research, there is danger that most statistical discoveries are false. And Yossi told me, you know, there's more to the paper than the eye meets. You should read it too. And we read it, and the point was that actually you could shift the paradigm. Instead of being interested in not making any error in all over the study, what was useful is the discovered one, the significant one. So what instead you can make this warning into the goal. And that was the shift, actually a very simple one, making this into our goal. And so design methods that control exactly this, the false discovery rate. So how do we define the false discovery rate? And I don't know if you can see there on the right, but it's the original page. If you take R to be the number of rejected hypotheses, number of discoveries, and V of them are in error, then if Q is the false discovery proportion, that is V over R, if you reject something and 0 otherwise, then the false discovery rate is the expectation of this procedure. And what is important that if there is nothing there, there's no difference between the 2 medications, the false discovery rate is the same as the previous used family-wise error rate, and so it makes sense to use the same 0.05. But it doesn't have to be so, and in fact, in genetic research, people use 0.10 and even 0.20 for the false discovery rate. It's really what you pay for the red herrings. And we also had a method that controls it, which looks at the 35 thing and the p-values that they have. Here I plotted the p-values from left to right, increasing in size, and on the left side you see the value of the p-value. The circles are growing with the p-values. And obviously, what you think is that somewhere here you have to cut, but you don't know where to cut, and say, those are the discoveries and those are not. And the issue is, where do you put the cut? And the idea was that, as you can see, those that are not related to true effects, they are mathematically known to lie on one line with the slope for which you can get an estimate 13. 13 of the effects are not true. And so instead of using 0.05, you can use 0.05 over 13. And now you put a line graphically, and you look for the largest point that can, where the point is above the line, and this is about here, and you get about 22. So this will be the first cutoff. And this was the paper we submitted back in '89. Okay? It went quite a long time, and along this way, we had to take the conservative one, which is go back, not estimate M naught, and use this line instead. And if you use this line and use the same idea of going until the first time that you hit, you see this is, the point is below the 9 after 9. And so in Niedermann et al., 9 periods are less than, and they turned out to be less than or equal to 0.01, are statistically significant at the FDR. And this is the idea of both the FDR and the methodology, the simplest methodology that deals with it. There are a lot of theoretical challenges in it. For the crowd at the back, I'll mention them. First of all, the original proof of the FDR that we gave in our paper was that the FDR is less or equal to the proportion of false discovery. We don't know it exactly, but it is under independence. And the outcomes in medical research tend to be positively correlated. That is, if the child is hyperactive, they also tend to be impulsive and so on. So there's positive dependence there. So an important contribution there was the one with Daniel Yekutieli, that under positive regression dependence for one-sided test, the BH procedure controls the FDR in the same way. And that's very important for practical implication. Tukey encountered 595 pairwise comparison between educational achievements in the US states, and that's a different type of dependency, and Danny will talk about it. Two-sided test under any correlation, there are indications that FDR is less or equal to Q. Some progress was made, and the question is open. Please don't be afraid to try your hands at it and maybe offer a proof of that result. Okay? Finally, dependency may be utilized by reassembly and knockoff and so on. There is a lot of effort going out in these directions, including very recent ones by Candes, Barber, and continue to work on that. I'm turning now to the microarrays problem, the FDR usage eruption. And new technology appeared in science, in genetic research, and that's microarrays. And that created a huge eruption in the use of FDR. This is the experiments where the gene expression were compared between two situations were made quite early in genomic research. And as you can see, in the beginning, it was done by hand, and therefore, very few were reported in a paper in a journal. Here you see one paper from a journal along the years, and that's the number of genes whose expression was compared in that paper. And that was about what was done. 1, 2, 3, that was the beginning. And then became the microarray invented, where you don't do it one at a time, and you do it in 91. The first time I encountered, somebody wrote to me a page, and there were drops on that, 96 drops on that, one for the control, one for the treatment, and was asked, what shall I do with that? And that was 96 already. Sorry, I want to add one more point. But the point is that with the increase, multiplicity was addressed for the first time only in 2001, when the number of genes that were measured was about 6,000. And then it erupted in Stanford, Berkeley, Tel Aviv, other places. We had methods that deal with this problem. That also brought the mixture model for gene expression, where you say that the proportion of genes that are not differentially expressed is P0, and you take a mixture of uniform for those that are not expressed and another distribution for those that are expressed. The importance of this mixture model is the fact that both Bayesian and empirical Bayes interpretation for FDR can be found. So in that sense, the FDR is philosophically robust. Every statistician can find his own FDR version and look at it. My other example is work that I've been working with Golani, late Golani, who passed away recently, and this deals with open behavior test where a mouse is tracked in an arena. And what you can see here is a big arena, and there is a hole up there, and from the hole a mouse picks out, okay? And as you can see, it picks out and goes back. And then this is the novel arena, and he explores it. And he walks out along the wall, and he makes stops, and he will soon return to there, and he will go in the other direction and make stops, and then he will find the fact that it is a arena, and he will have a few seconds, and then he will start going into the center. Okay? This is an extremely important test in neurology, in psychology, in development drugs, and because it deals with anxiety, say the proportion of time that he doesn't enter the center. It's a measure of anxiety. And we measure some 17 endpoints in this properties of this, and we used a lot of smoothing, robust smoothing methods there, because the dead mouse can walk 3 meters because of variation of the camera up and down. If you don't smooth it, you have the real problem. So we thought that we had a wonderful way of dealing with it. It didn't help with replicability, with the fact that in one lab, one strain of mice stayed more in the center, while in the other lab it stayed less. That's it. But we had this experiment in 3 laboratories. One of them was in the States, and that was Greg Elmer, and he took the mice on which he measured that, and then measured in 5 regions of the brain gene expression. So you have 27,000 genes, 5 brain regions, 17 endpoints, 22 million questions to ask in a single study. How do you deal with that? So the idea we developed was screening using strain difference first. Is there a difference between the strains? And then, once you discover a difference, you go back inside and test the 17 correlation by the pH. And we were quite successful with that, and that's a common display in this area, that you have the regions in the brain and the different genes, and here you have the 17 endpoints, and you have positive correlation green, negative correlation green, and those are the discovered one with false discovery rate of 0.05. But let's look at it, and that's what we did with Danny. Let's look at it a little bit in a more general way. What we did is we looked at the family of genes by regions, we had 135,000, and each one of them had tests of 17 correlation. And those are the rejected ones, and we continued only with the rejected ones. But you can see, look at this tree and build it all the way up and down, and look at more complex situation. And here you have the whole tree and levels of the tree, and you go down and you look at it at most generality. And here testing is done this way, and only those rejected you continue to test. The thing is now that the false discovery rate has a new point of view on that, because what are the important discoveries? If every discovery is as important, then you have 3-level FDR, you want to control those full circles. If some level is important, then you want to control the FDR only on this level. And if only endpoints are important, because once you looked at that and continue here, and you had the refined result here, then you have a different goal. And here comes a beautiful theorem by Dani, that if you assume independence across the levels and the models, then if you look at endpoints FDR, it is bounded by a multiple of the number of levels. If you look at a simple level, a single level, you cannot bound it, but you can estimate it. And by estimating, you can try to bound it. And for 3-level FDR, you have a bound which is 2 times 1.44 times the level of FDR that you are controlling at each level. No constraint on the shape of the tree, on the number of levels, on its complexity. And this says a lot about our interpretation in science. Because if selective inference is controlled at every scientific study by FDR or by FWER, if meta-analysis addresses jointly similar studies that were done by different investigators but looked at them jointly, and selecting statistically significant leads to the following, then the science-wise FDR is controlled. Not most of discoveries can be false. And let me go to the example, go back and finish with the example that I started with. Actually, if you look at Needleman with the shed teeth and you see what did he measure, it had a very strong tree structure. Okay? It had, you accumulated feed effect in general, but you had full-scale IQ, verbal processing, teacher's writing. And full scale, you then had performance and variable. The verbal processing had 4. Teacher's writing had only these 2. So it's a complex structure, but you can try to use the idea of testing from above down. The problem is the theory before doesn't work. Why? Because full-scale IQ is not independent of these 2 IQs. Actually, these are combined into the full scale. So you need a new theory, and that was done, and I will just demonstrate it rather than say, since there is no independence, what you do is essentially the 3-level of FDR by Bogomolov, Peterson, Sabati et al. And the idea is that you look at the family, test with BH, and then look at the number that you've done. Look at the proportion of discoveries that you had in this level. You had 3 out of 3 continue with 0.05 and do their children with 0.05. So here you do it FDR with 0.05, and these are the rejections. With the verbal IQ, you do it, and actually none of them has further discussion. With the verbal processing, you have 2 out of the 4. So if you go to their children, you have to attenuate your pH with 2 out of 4 times 0.05. And you get this result. Looking at it together, I think you are convinced that even minuscule residuals of lead in the blood are harmful. And that's the point we were trying to make. So I will leave this for the students, but it is a very active area at this stage, and a lot of work is being done currently. And I will just finish with a statement that actually what we have seen in the microarrays is the industrialization of the scientific process made the scientific challenges more complex. Science is done by machines and not by hand, just like cars are done by machines and not by hand. And FDR methodology and theory were developed in response to such challenges. And new challenges would require new developments. Thanks.
Okay, so thank you very much. So I'm just going to continue. I'm not going to talk about the past. I'm going to talk more about, I'll start with the present, and then I'll touch also on the future, and mainly about the importance of FDR in two applications, replicability and conformal inference. So I will start with replicability. So the replicability crisis has been going on for more than 2 decades, and the concern is that there are too many published findings that are false. And there are various reasons for it. The statistical reasons, one of them is publication bias, like you see in the cartoon here, or it can be selective reporting, that the analyst actually is asking a lot of questions but is reporting only some of them, or other questionable research practices like p-hacking, etc. So there is a consensus in many disciplines that it is necessary to raise the standard of evidence, and the question is how. And what we were thinking of was to continue with Boyle's philosophy and to directly target replicability. So you have mentioned before that the p-value threshold, the typical p-value threshold is 0.05. There were people that suggested to do it at 0.005 instead, but this kills power. What we're suggesting instead is to consider false replicability claims and making sure that there are not too many of these. The thing is that the claim of replicability may be harder to establish, especially when facing multiple hypotheses. So there is an issue with power, and therefore it's so important to have as a criterion not the FDR rather than not willing to tolerate even one false positive. But if it's a ratio among the discoveries, we know that a small fraction only are not replicable, that's okay. So we need to first define what we mean by replicability. There are many definitions, but I think that all of them have to satisfy the fact that the definition is in terms of the underlying effects, the parameters. So it cannot be that one study discovered that the treated had greater outcome on average than the controls, and then in another study they observed also this direction. What you need is that the expected outcome among the treated will be greater than among the controls in both studies, and that will be proof of replicability. In addition, the procedure should take into account the fact that the underlying effects may differ. So otherwise it's completely useless if we know in advance that in both studies either there is no effect or there is an effect. And this is important because somebody may think that they can just split their data, discover in the first half and discover in the second half, but this is completely useless for applicability. And as you have mentioned earlier, it's best that the replication is done very far away. Okay, so I'm going to give one application that we did where we established replicability of findings, and this is in genome-wide association studies. So just the background is that we have cases, in our case it was type 2 diabetes patients, and there are controls, and they are being genotyped, so their DNA is being read, and you want to know where, which locations in the DNA are associated with the disease. So there are many questions that are asked. In our case, it was 2.5 million. And what typically is done in this field is that they actually don't want to tolerate any false positives. So they have a very severe, significant threshold for family-wise error control at the 0.05 level. So each p-value has to be less than 5 times 10 to the minus 8. However, they also recognize that because these studies are observational and we want to generalize, non-replicability is super important. So their common approach is just to corroborate afterwards the finding by another study. But this is a very conservative approach. So why not use the FDR instead? The frequentist approach that you have mentioned is that you have not true null hypothesis, and these hypotheses are fixed, and then you control the FDR, which is the expected fraction of false rejections, out of all rejections, conditional on the hypothesis states. But there is also a more elaborate model, the mixture model that you have mentioned also, that a priori the hypothesis states are IID with a null state probability that is approximately the fraction of nulls that you have. And the FDR then is the unconditional expectation of the fraction of false rejections out of all rejections. Arguably, this is a model that can work well with GWAS because GWAS are a lot. We have 2.5 million hypotheses here. So what we had was 4 cohorts, 4 different studies. And we had 2.5 million SNPs, genotypes. And what we aim is at replicability, so to find the SNPs that are associated with a disease in the same direction in at least 2 of the studies. And if we do a frequentist analysis, for example, we do BH on the no replicability null hypothesis at the 0.05 level, we discover 83 SNPs. So we have 83 discoveries, and these are the replicability discoveries out of 447 SNPs that have an association in at least one study. So we see clearly that, as we expect, that it's harder to discover replicated findings rather than just association, where association is what you typically do with a meta-analysis. So we have less discoveries, and therefore it's also important to have powerful methods for FDR control when you're targeting replicability. And indeed, if we do it with a more elaborate model, the mixture model, then we have more replicability discoveries. We have 219, and out of 803 with at least one association. Okay, so this was the part about the central role of FDR for replicability analysis. And now I'm going to move to the second example, which is conformal inference. So this is what we have now, all the talk about AI, predictive models. We have a machine learning algorithm, and we want to predict from that. So for example, in this example, we have images of animals, and we want to classify it to which animal it actually is. And we have a machine learning algorithm, we have a black box that outputs an estimate of the probability of not belonging in each class. So in this case, it's not a very good machine because it happened that actually probability of not belonging to the bird class is lower than to the cat class. And the point prediction is the class with the lowest estimate. So in this case, it would be a bird, which is unfortunate. What is done in conformal inference is that you're actually turning the point predictions into prediction sets with a probabilistic guarantee. So just to explain a little bit how it is done. So we have, in addition, a calibration sample of n images where we know their scores, the estimated probabilities of not belonging to the true class. And we, of course, know also in which class these images are. And now we have our new image X. In this case, it's this cat image. And we can look at where the score stands relative to those in the calibration. And from that, we can compute also how extreme it is relative to the calibration, if truly it was a bird, or if truly it was a cat, if truly it was a dog. Now, we can use, so these are the conformal p-values. They are capturing how extreme this example is. And based on that, we can actually move away from the point prediction and get a prediction set, which will be all the classes for which the conformal p-value was greater than alpha. This will give the guarantee that the probability of the true label being in the prediction set is at least 1 minus alpha. And in this case, it will be bird and cat, and the true class is indeed in this set of containing both bird and cat. Okay, so this is conformal. So this was conformal inference for just one example, and it's very standard to use it nowadays. But what we are concerned is the fact that we don't have just one image. We usually have a group of images. So we have m images, and m can be hundreds or thousands or more. Now, if we build now prediction sets that have probability of covering the true class with probability at least 1 minus alpha, then we expect among that the non-coverage will be only alpha, which is okay. So if alpha is 10%, we expect only 10% of our prediction sets not to cover the true class. The thing is that not all prediction sets are of interest. And there comes the problem that the analyst will actually select the ones that seem important to her. And among those selected, the expected fraction of non-covering prediction sets may be much larger than alpha. So we will have more errors among the selected. And just to understand it intuitively, here what we have is 30 images of animals. They can be only, there are only 3 classes. We know that the image is either a bird, a cat, or a dog. And then we build prediction sets with the conformal prediction at level alpha, which is 0.1. And you see here in yellow the prediction sets for each image. But the thing is that some of the images are some of the prediction sets are completely trivial, because it says, okay, the image is of a bird, the true label is within bird, cat, and dog, but this is something that the analyst knew already in advance. So this is not interesting. And we also know that we have 3 errors out of the 30. But now the analyst takes away those non-trivial, he selects only the non-trivial ones. And he's left with 20 images that are of interest. But then within these 20, the false coverage proportion is already 15%, not 10%. So it has increased. So among the selected, we no longer have the guarantee that we had without selection. So what we want is procedures that target the expected false coverage proportion, which is the expected fraction of non-covering prediction sets among the selected. This criterion was suggested by Benjamini and Yekutieli in 2005 for confidence intervals on selected parameters, and Danny will talk about it soon. So their solution was use the level alpha times the fraction selected. So if we go back to our example, we had alpha of 10%. We selected 20 out of the 30. Now we can build prediction sets at level 2/3 times 10%. The thing is that once we build a prediction set with a lower level, the prediction sets are wider. So now among the predicted, we may again have trivial prediction sets that are not of interest. So a little bit more clever approach has to be taken, and we've done it in this paper. Okay, and I'll just conclude with another typical selection in when we have a lot of examples in conformal inference, and this is excluding a non-interesting class. Suppose we're only interested in mammals, we're not interested in birds. So we want to exclude the images of a bird. So we can define it actually as a hypothesis. So the null hypothesis is that this image is of a bird. And we can have conformal p-values for these family of hypotheses. And we can apply the BH procedure on these conformal p-values. And it's really nice that even though the p-values have conformal dependence, these family of hypotheses are random, the FDR is controlled at the level alpha. In addition, after we have our discoveries from the BH procedure, we can take the discoveries and construct prediction sets at level alpha times the fraction of discoveries. And this guarantees now that the false coverage rate is indeed at most alpha, and all constructed prediction sets will exclude the birds. So to summarize this part, so what we see is that inference for M examples can be viewed as a multiple testing problem where the hypotheses are random and the p-values are dependent. And the FDR and the FCR criteria are extremely useful for reliable conformal inference. And one last thing. So this is the future part. About optimal multiple testing. So the classic approach for devising multiple testing procedures is that you have an error criterion such as the FDR, and then you ingeniously think about a procedure for actually controlling this error criterion. For example, the BH procedure, so that you really want to have as many discoveries as possible, but without violating the error. And then you examine in simulations the power of your procedure, and you see that it's good, you publish, and you're happy. But if we think about a single hypothesis, then what we have in a basic statistics course is the Neyman-Pearson lemma, right? We have an objective, which is to maximize power. We have the constraint that the probability of a type 1 error should be at most alpha, and this actually dictates how the test looks. So why not do that also for multiple testing? And so the generalized Neyman-Pearson approach formulates an optimization problem. You maximize the power objective, which can be the expected number of true positive findings, while guaranteeing an error constraint, which can be the FDR. And now you have your power objective, you have the error constraint. It actually dictates the policy, the optimal policy, the best that you can do. And this is your multiple testing procedure. And what is really nice is that if you assume that the mixture model, then this can be solved, and you can actually have an optimal solution. And this is because mixture model assumptions are very reasonable, both in conformal inference and for GWAS applicability. I think it's a very fruitful place to work and to get procedures that give us even more power, the best power that can be. And that's it. I'm working in these three fields of research. These are my wonderful collaborators on each of them. And thank you very much.
Thank you very much. Hello, everyone. Thank you for coming. I'll postpone my thanks for later. Okay. It's always good to start a talk with one of John Tukey's work. Especially in this case, it's even relevant. Okay. So in this work, maybe see the slides. In this work, John Tukey and his colleagues, Williams and Jones, studied the Bonferroni procedure, the Hochberg procedure, Yossi Hochberg, and the B8 procedure. And they run simulations, and what they want to see is if these three procedures actually control the FDR for testing pairwise comparisons. And the underlying message, the takeaway message is we recommend using the B8 procedure for testing pairwise comparisons. Okay? So for us, statisticians, professional statisticians, multiple comparisons people, this is a bit of a statistical mystery. First of all, the more petty questions. Shouldn't the Bonferroni-Hochberg procedure be used to control the FWER rather than the FDR? Why doesn't Tukey recommend Tukey post-hoc analysis for pairwise comparisons? And does the BH procedure actually control the FDR for testing pairwise comparisons? These are more petty questions. The more fundamental questions are, should we control FDR for post-hoc analysis, which is what you have talked about, the original work by Tukey and Shafet? And if you can actually control the FDR in post-hoc analysis, what does it leave for the family-wise error rate? Are there cases in which we should consider controlling the family-wise error rate? Okay. 2024, ask the expert, ChatGPT-4. The question is not very well formed. This is on me. What is the difference between post-hoc analysis and FDR? So answer, post-hoc analysis and FDR, false discovery rate, are both important concepts in the context of statistical hypothesis testing, but they serve different purposes. So this is correct, but not very useful. So there's a lot more. It's very diligent, the ChatGPT. It gives you lots of text very quickly. Often, researchers may perform post-hoc analysis after an ANOVA and use FDR to adjust their p-values for any multiple testing they conduct subsequently. So this is more specific, but not true. Okay, so to try to answer these questions, we'll move on to work by Yoav and mine from JASA from 2005. This is the paper. And what we say in this paper, we argue that two types of problems can arise when providing inferences for multiple parameters. The first one is simultaneous inference, which is simply the need to provide valid inference for all of the parameters. The other type of problem is selective inference, which is the need to provide valid marginal inference for parameters that are selected after viewing the data. If we look at Tukey's post-hoc analysis to understand this distinction, then this is post-hoc analysis. This is what it looks like. Some notations, I mean, this is a statistics talk. Sorry about that. Mu1 to mu k are k treatment effects with corresponding subgroup means, estimates, which are these mu1 to mu k hats. These are the estimates. When we run analysis of variance, we may reject the null hypothesis that there's no difference between these treatments. The Tukey's honestly significant difference method uses a standardized range distributions and I just want to mention this Q tilde hat is just a fixed value you get out of a table, out of the computer. It is the range of k t statistics. The only thing you have to understand is that the bigger the k is, the bigger the range, and these are bigger values. And they can get, we'll see later, as big as similar in size to Bonferroni critical values. If we want to do post-hoc testing for pairwise comparisons, then we reject the null hypothesis that the two treatments means are equal. If this standardized difference, I'm sorry about this again, the standardized difference is bigger than this quantile of range statistics. And if we want to construct confidence intervals, we use the same kind of idea. We take the actual estimated difference plus minus the standard error times this critical value. Okay. And the Tukey's HSD, how is this connected to simultaneous inference? The idea that the main, maybe I skipped this. So this is what he suggests. And how is it connected to simultaneous inference? The idea is that simultaneity ensures valid selective inference. The actual property that Tukey's procedure ensures is simultaneously coverage property. That means that if we think about the probability that for each of the individual treatments, the actual treatment difference is inside the corresponding confidence interval, then we have this property for all the different k over 2 means. And because we have this simultaneous inference, it ensures that for any pair of treatments that may be selected post hoc, then either the marginal test or the marginal confidence intervals are valid. So we have these two different properties, and we use the property of simultaneity to ensure selective inference. Okay. The question is, can we use the BH procedure for post hoc analysis? Suppose that the post hoc analysis is comparing the effects of the best and second best treatment. We look at the treatment's effect. We can't look at the treatment's effect. We estimate them. We take the biggest estimated effect and the second biggest. This is pi hat k minus pi hat k minus 1. The level alpha BH procedure for a family consisting of just one hypothesis is reject the null hypothesis, that is, make a discovery if the p-value is smaller than alpha. This is just a marginal test. BH for 1 is just marginal test. Thus, the post hoc analysis for the single difference with the BH procedure would be, let's reject this null if this standardized difference is bigger than a t statistic, a marginal t statistic, which is, of course, doesn't conform with what Tukey suggests. Tukey says if we have k bigger than 1, if we want to do post hoc analysis, it won't work. So ChatGPT, in this case, is incorrect. And it means that if we actually want to apply a BH procedure, FDR, we need a more organized way to think about selective inference. Okay. And again, we return to our work. And in this work, we also suggested a selective inference framework. Okay, so now we have different parameters. These theta 1 to k, these are parameters, and they are the differences we had in before. So the differences between two treatments are now thetas. For each theta, we have estimators. The t's in this case, we use to estimate the thetas. And we construct, and the idea, what do? The goal is to construct confidence interval for the selected parameters. That is, we look at the data, we look at T1 to Tm, and we have a selection rules. After we look at all the data, we decide which parameters we want to select. And what we suggested is that we use the false coverage statement rate, the FCR, as the measure for the validity of confidence intervals constructed for selected parameters. The idea that FCR looks the same as the FDR, but instead of number of discoveries, we have instead of R is the total number of statements we make, which is the number of confidence interval we construct. And instead of V being the number of false discoveries, now if you construct a confidence interval, a false discovery would be we have the confidence interval, and it's not a good confidence interval if the parameter isn't inside it. So we have a way of extending the idea of an FDR to more general statistical inferences. Okay, and then we also say, okay, we have the FCR. How do we control it? So the idea that for any selection rule we have, and look, no p-values. We don't necessarily have to have p-values. We just have to have a selection rule that if we have independent statistics and we select our parameters out of M, then all we need to make is make the level of the coverage rate of the confidence interval bigger. If a regular confidence interval would be 95%, what we call 1 minus Q, then if we select R out of M parameters, then we just have to make it bigger accordingly. Okay? And this is our general solution for constructing confidence interval after selection. And why does it move? Okay. I think I skipped a problem. Okay. So how do we actually apply this solution for testing pairwise comparison, or for doing post-hoc analysis? So the idea that for valid selective inference, we need to specify which pairwise differences are selected out of all k times k minus 1 over 2 pairwise differences, following a ANOVA rejection of the complete null hypothesis. That is, if, for example, we say, okay, well, let's construct confidence intervals for all m pairwise differences, then we simply construct the same confidence intervals as we would regularly for all the pairwise differences. But if, for example, we're saying, okay, look, I'm only interested in a particular difference. For example, the difference between the best treatment and the second best treatment. In this case, the confidence interval will have to be much bigger. How bigger? In this case, R is 1, and the confidence intervals we construct are actually Bonferroni confidence intervals. And in general, the more we select, the bigger the less we select, the bigger the selection is. We have to pay more in terms of increasing the size of the confidence interval. Okay. What about FDR? If we want a valid FDR control post hoc, then we do marginal tests at either level alpha if we select everything, or alpha over 1, m if we only select 1. Okay. And the interesting idea for us statisticians, that this particular case works even though these are dependent statistics which shouldn't work for pairwise comparisons. Okay, so how does FDR measure, or what's the difference between FDR and post-hoc analysis? Not what's the difference, but the idea that we have the same objective, but a different setting. Post-hoc analysis is concerned with valid marginal inference for pairwise difference, or in the case of Chaffee, contrast, when we do the ANOVA, and then we cherry pick at our will the differences or contrasts we're interested in. FDR, it's a different setting. The idea that FDR control is used in modern applications, GWAS, fMRI, non-parametric regression, whatever you want, that are concerned with providing correct marginal inference for multiple parameters that are selected after first considering a pre-specified of M parameters. The idea you have to pre-specify what you're initially interested in. Okay, so it has to be more structured. Okay, important, and of course, going back to Tukey, does Tukey not know his craft? Of course he does. It's important to note that Williams, Jones, and Tukey suggest directly applying the BH procedure to all pairwise differences. Okay, they're not cherry picking. They're interested in everything a priori. Okay, sorry, I made a mistake. They're interested in. They're not doing selection, but rather they're doing the BH procedure to find discoveries out of a pre-specified set of M pairwise differences. Is this theoretically valid? That's an open question. Okay, so I think it is, but this is again for the younger generation. Okay, I think I messed up. Sorry about this. Okay. As promised, an example where so I said FWE, what's it good for? Okay. So I said in the post-hoc analysis, you don't necessarily need it explicitly, but in general, FWE or simultaneous control for post-hoc analysis offers selective inference. What I want to end with is an example in which simultaneous error that we actually need to control for family-wise error per se. So consider a clinical trial that compares a new treatment to an existing treatment on M subgroups of the population. Where the effects of each treatment may be different in each subgroup, and the new treatment is supposed to have larger effects. PI, again notation, is the p-value testing equal treatment effects. Effect null versus the alternative hypothesis, the effect of new treatment is larger in the ith group. Okay? And the main thing in this problem, in this particular setting, is that replacing existing treatment with new treatment in a subgroup can be done only if it has a larger subgroup effect. So in this case, it makes sense to guard against making any erroneous decision in any of the subgroups. Okay? So in this case, by all means, apply a family-wide error rate controlling procedure to the p-values. Okay? So in this particular case, it makes sense. This is what we want to do. Simultaneous inference per se. Okay, again, sorry about that. Conclusion, I'm done. Simultaneity is a direct result of dimensionality of the parameter and may be generally addressed with appropriate choices of the loss functions. This is the easier problem to deal with in terms of statistics. FDR, FCR are frequentist measures of probabilities of making erroneous marginal inference. And I just like to stress this, why this term FDR is so important in modern days. Usually, still, I guess, in the New England Journal of Medicine, if you want to find something important, you look at the p-values. This is important. Why is this important? Oh, the p-value is 0.0001. Wow, this is a great finding. It doesn't work for large data. We know that you can't count on significance if you're measuring lots of stuff. Now, when you ask a biologist, you did a big study with genetics, is this a good finding? He said, wow, this is great. I have an FDR of 0.0111. Sorry, my breast mic. 0.001. Okay, so the FDR is the central concept in interpreting big data. And about selective inference. Selective inference is a general problem that may take on many forms. Post-hoc analysis, model selection, etc. And it even has a seminar, an online seminar, the International Seminar of Selective Inference, every Monday on the web. And the BH procedure, and what is goal of the BH procedure? Plain selective usually the goal of the BH procedure is the selection rule for making the selection. And by this I'm done. Thank you for your patience.